are live. Nice. All right. Okay, I'm gonna get started then. So, fun. Can I like split the window or oh, I can split the window. Let's split the window. Give me a second. There we go. Now I can see the chat and the presentation at the same time. That's awesome. Okay. Well, welcome to Functional Programming 101. This is going to be a fun workshop because there is so much more content than I initially thought there would be. So yeah, this is going to be a bit of a trip. Have fun with that. Now then, I'm going to ask a question before I get started. How many of you know what functional programming is? Okay, the question is, do you know what functional programming is? Just to the question, so I can get an idea of like your okay. Most of you have not. 2 of you have. Of course, Matei has. That's fun. Okay. Functional programming is not dynamic programming, though you can do dynamic programming pretty well with functional programming. It's pretty nice. But anyway, let's get started. Okay, let me actually move the slide forward. So before I can answer this question, a lot of you are probably asking this question. Why the hell are we doing this in the first place? So a little bit about what functional programming is. It's a different type of paradigm. You all when you all started coding, you probably got started off with a language like Python or Java, where you have to be very specific about like what you want the computer to do in order to get it to do it. But functional programming is something in which you don't have to worry about that as much, if that makes sense. I know that's kind of weird, but it'll start to make sense a little bit later. But why use functional programming? Here are the benefits. It's easier to reason about what you want your program to do. It's insanely powerful if you know how to use it. It's good for multi-threading because functions don't interfere with each other, and it's easier to debug. So there's that. Cons? Hell of a steep learning curve, as you'll see later. You like math? Lots of that. lots of abstract algebra, and it's most functional programming languages, I think, are slower than typical programming languages nowadays, but that might change in the future. But who knows? Anyway, any of you have ever used React functional components? That's an example of functional programming. Or JavaScript actually has some functional features embedded into it because it's based off Scheme. So if you've been to my JavaScript workshop, you'll know that. So we'll get into those in a little bit. Anyway, so let's talk about programming paradigms. That guy, Alan Turing, you know who he is. So he came up with the idea that you can carry out any computation using a Turing machine, which is basically a machine that measures state by like punch cards or something. Not entirely sure about how it works. I haven't taken CSE 105, but state. Turing machines use state. However, there is a different computing paradigm that is actually a little bit older than Turing machines. That's invented by this guy, Alonzo Church. It's called lambda calculus. So lambda calculus is a really, really weird thing where you essentially define variables and functions, and you chain them together, and you can do all sorts of stuff with it. What kind of stuff? The same stuff that you can do with Turing machines. It's crazy. Yeah, so this lambda calculus thing is the thing which all functional programming languages are based off of nowadays. By the way, brownie points if you can tell me what this formula is and what it means. Matei is probably the only person who can answer this question. But anyway. Whatever. So what is functional programming? It involves functions. Wow, amazing. But yeah, functions. Oh yeah, the checking code. I forgot to mention the checking code. It's in the shared notes. It is f of x. That is the checking code. Anyway, yes. So, functions. But what does that mean? What the hell is a function? Okay, so I'm going to take 2 minutes right now. Y'all can give me any properties you can think of in the chat. I'm just going to dedicate a couple of minutes to that. Yeah, input and output, good. Runs an instruction set is an interesting one. Each output does not. Oh, I know what you mean. Yeah. Okay, that's good. All right, chat seems to have died down. So y'all have basically got the gist of it. So it should only operate on inputs. So yeah, it has functions have inputs and outputs, and the output only depends on the input. Bryce got that. No, Bryce was right. It has to return an output. So you can't have in functional programming, you can't have a function that only does stuff. So one big idea that I'll come back to over and over again is that functional programming has no side effects. What does that mean? It means that a function can only operate on its inputs. It can't do stuff on the side. It can't, for example, printing is a side effect. Changing global variables is a side effect. Yeah, can't do that. And one important feature for functions is that no matter how many times you give one particular kind of input, it always gives the same output. Or as Sumit would put it, it has to be deterministic. I love this GIF, by the way. This is great. Anyway. Now you might be asking, what the hell? No side effects? Don't programs kind of need side effects to work properly? Yeah, they do. You can't exactly have a useful programming language that doesn't operate on some kind of outside thing. Like you can't, if you had no side effects, you can't print, you can't read files, you can't do useful stuff. So I'll talk about briefly how functional programming languages do this at the end, but it's a really complicated subject. So I'm probably not going to do it justice today, unfortunately, but I'll touch on it for sure. Where was that, Ishan asks? Oh, this was at the trivia night. Trivia? Jeopardy. Yeah, we had a Jeopardy event last year. That was really fun. Anyway, so let's talk about JavaScript. I mentioned earlier that JavaScript has some functional features. So let's take a look at how to change numbers in an array. Oh my god. So on the left, you have the typical approach. Say you wanted to add 1 to all the numbers in the array. Well, how you do that normally is you'd have a for loop. You'd go through every number in the array, and then you just add 1 to it. You all understand what this code does. Now take a look at the code on the right. This function map takes a function, and this is called a lambda. I guess you could call this a lambda. This is an arrow function, but it acts like a lambda. What a lambda is it's an anonymous function. It doesn't have a name. It lets you define functions in line, and what this function does is that it just adds 1 to whatever it puts in it. Now then, so what this does is that it takes nums, takes all the elements in num, and adds 1 to it. But key difference is that it does not change nums itself. If you ran this ran this, and then check the value of nums, it would be the same as it was before. That's a very functional thing because you're not editing the original array. You're returning a new one instead. Anyway. Well, I forgot to hide that crap. Okay. Well, this is going well. Give me a second. Let me change that real quick. Hold on. In my defense, I was up at like 5 a.m. trying to get the content right, so I forgot to add a couple of animations here and there. So be right back, and I will get that in order. Okay, let me get the presentation back up. Present. Where's the present button? Oh, god damn it. Bam. Okay, let me get the screen share back up. God damn it. Chrome tab, functional programming. Here we go. Okay. So let's take a couple of minutes to try this. Not showing up. Come on. Come on. There we go. Okay. So here's a challenge for you. So now that I've introduced what the map function does, so it's a property of an array, and you take it, you give it a function, and it'll do that function to everything in the array. Now, here's your challenge. Add 1 to only odd numbers. Now then, yeah, feel free to use Node.js, use your browser console, use whatever you're comfortable, use whatever your go-to option is to run some quick JavaScript code. I'll spend a couple of minutes on this, and then we'll get back to it. And I'll be here if you have any questions, obviously. I go back to the previous slide. Yeah, Mateo's got the right idea. Maybe don't post the answer in chat though. let people think about it a little bit first, you know. All right, I'm just gonna move on now that the answer is out and about. So here's what I did. God damn it, Mateo, no. Okay. Anyway, so I did everything in line. Obviously, you don't have to do it this way, but you guys need to take in mind basically do the same thing. Mateo, I can hear your keyboard, by the way. So function. Function takes a number, checks if it is divisible by 2, and then if it is, return the number, and if it isn't, return the number plus 1. Pretty simple. Okay. Yeah. All right, cool. Moving on. So map is an example of what's called a higher order function. A higher order function is a function that takes a function as an argument. So let's talk about some other examples of higher order functions, and we're going to be using a lot of these today. So filter is another higher order function. What filter does is that it takes a function that returns a Boolean, true or false. And if that Boolean is true, it will keep that element in the array, and if it is not true, then it will just take it out. Reduce is another higher order function that condenses an array into one single value. So what this function does is that it sums up all of the numbers in the array, and it does this by using this function. So this function in here is what's called this function takes two values, the first of which is called the accumulator, and the second one which is just the value. No, it's in shared notes, yeah. Anyway, yeah, so what's doing here is that sum is the total accumulated value of the reduced number so far, and it just adds x to it. So every time it gets to a number, it checks the previous value of the accumulator, and then it adds x to it. So it'll add all of the values in x in the array. Next, oh my god, I'm so stupid. Okay. Give me 1 second. I'm clean, dude. Oh my god. I hate my life right now. God damn it. Fuck. Oh, I cannot swear on stream. That's bad. That's really bad. Oh my god, this is a mess. Okay. Hold on. Let me make this real quick. I swear this is the last one that'll be like this. I'm pretty sure I did everything after this. Back to the presentation. So, okay. Now that I've introduced filter and filter and reduce to you, assuming that you don't remember what the answer looks like, try adding up all the numbers less than 10 given an array. Oh my god. Oh, I should put the link to the slides in the shared notes. It is acmurl.com/lambda slides. So if you want to look at the answers, they're in the slides. Don't actually, please, but. Custom poll. Okay, I'm going to try using this feature to check if you're done. Dope. Hmm. Not getting a lot of responses. Hmm. That's okay. There's not a lot of people here. All right. Thanks for coming, Bryce. Anyway, in the interest of time, I'm just gonna move on because I've got a lot to get through. But yeah, there it is. So, um, what I've done is I've chain filter and reduced together here. So, first, what I do is I take the. I apologize for the terrible ending, by the way. That was kind of a mess. But first, I take the array and I filter out all of the elements that are less than 10. After that, I just add them up. So, yeah. Okay. So though JS has a lot of has some functional features, it's not perfect. So I can't. Some things I can't do. I can't make a standalone function. Map is not a standalone function. It's a function. It's a property of array, and I can only do the map function on arrays. So if we want these functions to be able to like, the idea behind functional programming is abstraction. So you want functions. You basically want to be able to like apply functions to everything. So yeah, here we go. Can we do better? Yeah, we can. I'm going to talk about Haskell. Oh God. Obviously, Haskell is not the only functional programming language out there. There's OCaml, there's Scala, there's a whole bunch. But Haskell is the one I'm familiar with, so I'm going to talk about Haskell. Well, if you know one, you know a lot of them. So because all the syntax is pretty similar. But yeah. So side note about this comic right here. Facebook actually uses Haskell for the spam filters, fun fact. So pretty cool. So to run Haskell code, if you don't have Haskell on your computer, just click on the link. That'll take you to an online editor. But yeah, you can also install it here if you want, but that might take a little bit longer. So just, yeah, I would recommend using the REPL. And this is the part of the presentation that gets weird, and I mean really weird. So please ask questions if you have any, because this language looks really strange to people who have not seen it before. So it's going to be pretty alien. So just let me know if you have questions. Please let me know if you have questions. Okay, moving on. So stuff about Haskell. That's a comment. You have your typical variables, integers, characters, strings, lists. I apologize for the inconsistent coloring that's going to be in this slide, by the way, because my syntax highlighter doesn't have Haskell. So that's fun. Okay, first Haskell thing. You can really easily define types. That should be data. That word should be data. Oh my God. God damn it. So you define types with the keyword data. It should be data. But yeah, you can define a type called name. which is just a string. You can define a type called age, which is an integer. You can define a type called person, which you can combine types like this. So if you were to define a variable that contains information about me, this is how you would do it. Yeah. Everything is immutable in Haskell and most other functional programming languages. So you can't actually change any of the values once you set these. Yeah. I believe in the REPL, there should be an interactive terminal. You can't actually edit values in the interactive terminal, but if you write Haskell code and you assign a variable twice, you'll get an error. So just be aware of that. Okay. Talk about functions. Okay. Haskell functions are a little bit defining Haskell functions is going to be a little bit strange to people who haven't seen this kind of notation before, but it's pretty. It gets pretty intuitive once you start to understand it. So here I'm defining a function called add. Here's the function signature. Think of the type on the very right is the output, and all the types to the left of it are the inputs. So that keyword should be integer, by the way. Oh my god. Anyway, so add is a function that takes two integers and returns an integer. So add xy is x plus y. Here's a conditional function that returns if a number is even. So takes an int, returns a boolean. So to define functions that have conditions like this, you use something called guards. This is how you do that. So even x, so if x mod 2 is 0, you get true, and otherwise false. Pretty simple. All right. Here's another functional programming language concept. So if you have a function that takes in two numbers and returns a number, you can also think about it in a way such that it is a function that takes one number and returns a function that returns a number. That is weird. That is really weird. That is probably not a concept you've ever heard about before if you don't know about functional programming at all. But it's called currying, and it's named after the same dude Haskell is named for. His name is Haskell Curry, which is an awesome name, by the way. I want to be called Haskell Curry. But yeah, here's a function, add 3. And by applying just the number 3 to add, which normally takes two integers, what I've done is that add 3 will create another function that will take an integer and add 3 to it. So 3 is an integer, and it returns integer to integer. So if you type this out in your REPL in the interactive terminal, and you try adding using this function with numbers, it'll just add 3. You can also do this. So plus is actually a function. Plus is what's called an infix function. So the way you're used to doing binary operations, you do like 1 plus 2, 3 plus 4. That's called infix, where the operator is in between the two operands. By default, Haskell uses, I believe it's called postfix, where the two operands are after the function, so the operator. So yeah, plus is infix, but if you add 3, this will, yeah. The equivalent in JavaScript is kind of strange. So this is what's called a closure. So it's a function that returns a function, and what this does is that you can see that add 3 takes a num and it returns a function that it shouldn't be called add 3, it should just be called add num. But what this does is that it returns a function that returns it returns a function that when you pass in a number to it, it will return the number plus whatever number you passed in. That's a little weird. Okay. I'll come back to this idea later, but more on Haskell. So you could also have, so we talked about higher order functions earlier. This is how you define a higher order function in Haskell. So parentheses make, I've drawn parentheses here to make it more clear. This is the reduce function that we talked about earlier when we were still doing JavaScript. So reduce is a function that takes a function that goes from type B to A. Wait, what? Reduce is a function that takes a function, a number, and a list. So this function is the function that actually reduces the array. So remember from earlier that the function that reduces the array takes two variables, one accumulator and one representing the element in the list. So in the case of sum, what this does is that it just adds it up. So yeah. B, this value of type B right here is called the initial value for the accumulator. So in the case of summing up elements in the array as before, the initial value is obviously 0 because the sum of an empty array is going to be 0. It just doesn't make sense for it to not be 0. So yeah, and square bracket A is an array or a list of type A. So reduce takes a function that takes two numbers and outputs 1. Well, not numbers. B and A are any type, but takes a B, A, and returns B, and then takes an initial value of type B, an array of type A, and then it outputs a value of type B. That's whatever the accumulator ends up to be. So, stuff to talk about here. So this is also probably a little bit alien to anyone who has not seen Haskell code before. This is called pattern matching. So depending on what the parameters of your function look like when it's called, it will what Haskell does is that it will trigger different branches, I guess, if it recognizes a pattern. So here's the base case. So if I have nothing here, wait, that should be empty. Crap. Okay. Anyway, so obviously we have a case where the array is empty. If the array is empty, we return the initial value for the accumulator. However, if we have a function, an initial value, and a list. Oh god, there's a lot I have to explain here. So this is the list, but what happens here is that x is the first value in the list, and x's is the rest of the values in the list. So this colon operator splits a list into its first value and the rest of its values. So that's what it does. And what this does is that it will call reduce on f, and then it will apply f to the accumulator and the element in the array that we want to add to the accumulator, or just do stuff to the accumulator. And here's the rest of the array. Okay. Now all right. Now the reason I had parentheses here instead of square brackets, because this is an array after all, is that this evaluates to this. Remember that f is a function that takes an accumulator and a value, not an accumulator and a list of values. So that is not going to compile, just so you're aware of that. Let's talk about function composition now. So you know how in math you can compose functions by taking the output functions and applying them to the input of other functions. Well, you can do that here, and it works the same as it does in regular math. Cascade of functions like that will evaluate to that. And in Haskell, you can compose functions like this. So this is equivalent. This is equivalent to that. Okay. Loops. Did I forget to add what loops are? No, I didn't, because they don't exist. That's going to be fun. So there are no loops in traditional functional programming languages. Instead, you only have recursion to work with. So yeah, that's going to be interesting. So here we have a couple of example functions that I've written. So here's a Fibonacci function. Fibonacci takes an integer and returns an integer, and it returns the nth Fibonacci number. So what is the nth Fibonacci number? Well, we define it recursively. So fib0 is 1, fib1 is 1, and fib n is fib n minus 1 plus fib n minus 2. So if I do like fib2, for instance, fib2 will be fib1 plus fib0, which is 1 plus 1, which is 2. Okay. So here is, this function here will sum up a list of numbers. So what it does is that if the input argument is empty, it will return 0. And if I have a list with items in it, it will split the list up into its first element and the rest of its elements, and we compute the sum recursively. So we add x to the sum of the rest of the list. Okay, cool. Oh my god, I did it again. Oh my god. Oh my god. Okay, this is a mess. I'm sorry. Okay. I'm hoping that you don't remember what this looks like, because your next challenge is to write a function that computes the factorial of whatever you put in. So yeah, I'm going to give you a couple minutes on that. And I just remember that, okay, I should probably pause the recording every time I get you to do something. So I'm going to pause it now. All right, we're being recorded again. And I'm just going to go over the answer and demo it in the REPL so that you can actually see how to use the REPL, because I forgot to teach you how to use the REPL, which is kind of my fault, but oh well. So here's the factorial function. It takes an integer and returns an integer. And factorial of 0 is 1, and factorial of n is n times factorial of n minus 1. So I'm just going to go over how to use the REPL real quick, because I need to do that. So let me see if I can find it real quick. Here we go. Get rid of this, clear that. Share my screen again. Oh, that's my webcam. Jeez. And here we go. So let's create and run this factorial function while we're at it. So it's going to look a little weird because it's half my screen, but it is what it is. Sorry. So we have factorial. You are right. Factorial n minus 1. And I'm going to put the main equals bootstrap line blanking, so it doesn't complain that main doesn't exist. And there we go. Now if I run factorial 3, it should give me 6. Cool. Is anybody still confused? I'm not getting any responses, so I'm going to take that as we're okay to move on. So, okay, give me 1 second. All right, moving on. Now, challenge part 2. So remember how the map function was defined earlier? It's a function that takes a function and an array and returns an array. Well, let's try writing the math function. I'm gonna see if I can make it easier on you this time. I'll give you the function signature so you can actually write the function based on that. So what it should look like is map f hold on, type A to B, and it should B to A. All right, I put the function signature in the chat. Now, okay. Hopefully you should be able to go off that. If not, I will explain. And I'm gonna put the same poll up, and I'm gonna pause the recording as well. Okay, we're being recorded again. Yeah, but anyway, yeah. Here's the map function. We're back. Here's the map function. I'll go over it again. It's a function that takes an array. It's a function that takes a function that's from type A to B. That's an array of type A. That's an array of type B. And maps one to the other. So map f of So base case, empty array, maps to empty array. Array with items is function applied to first item combined with map applied to the rest. Okay, back to trees. So no one has any questions about trees? Yeah? Okay, cool. This is how you insert into a tree. So here's a function called tree insert. It takes this, what this is here, this restricts the type of A to something that can be compared. So that's so that I can do stuff like double equals, less than, greater than. But yeah, so tree insert takes a tree of A, tree of type A. It also takes the value to be inserted, which is a type A, and it will turn a new tree with the inserted item. So how this works, pattern matching again. So if the tree we're inserting into is empty, it will return a tree with the element inserted and two empty subtrees, left and right. So, but if the tree we're inserting into has values, it'll look like this, and we have to compare the element we're inserting into the value that's already in there. So if they're equal, just replace it. If what we're inserting is less than the value of the node, we go left, and if it's greater than the value of the node, we go right. No problems here? All right. Next challenge. I actually remembered to hide the text blocks, but your next challenge is to write a function that will check if an element is in a tree. So I've given you the method signature. This should be helpful because it looks kind of similar to tree insert, except it returns a Boolean instead of a tree. But yeah, here's the method signature. I'll give you a couple minutes to work on that. Please ask questions. Cool, we're back. And here is the rest of the function. So William mentioned that you can base it off the insert function, and it does look kind of similar because they both recurse in the same way. So here you have a tree. Here you check if the element is in the tree by okay. So let's take a look at the base case first. So is an element in the tree if the tree is empty? No, right? So we return false. If the tree is not empty, however, we need to check our three cases. So if the element we're checking is equal to the element in the node, then we return true because we found it. Otherwise, we check if element if we check if the element is in the left tree and the right tree. We check if element is in the left tree if the element is less than the value in the node, or we check if the element is in the right tree if the element is greater than the value in the node. So there you go. Anybody have any questions about this? No? Okay, I'm gonna move on then. I was gonna dedicate this time for you to mess around with the functions I just gave you, which is probably a good idea since I haven't been doing that until now. So here's a tree that I've written out, and feel free to play around with the two functions from before, and see if it works. I'm going to dedicate a couple of minutes to that too. Just let me know if you have any problems. Okay, I'm gonna just move on now. All right. Okay. This is the part of the presentation where things start to get like really abstract. So I've talked about mapping arrays. We can map other stuff too. So that's what functors are. So okay. A functor is a type where this fmap function is defined. And this fmap function, what it does is that it will map a functor of one type to a functor of another type. So yeah. What we can do is that we can, okay, if we define a, I don't even know, if we define a type as a functor, we have to define an fmap, and what the fmap does is that it will map functors of one type to functors of another type. Here's how list is a functor. List is a functor where fmap is just map. Map is what we already know, because you can use map to map an array of one type to an array of another type. Now then, I had another exercise here. And of course, I forgot to get rid of the text boxes for that. Oh my lord. But okay. But yeah. Thanks, William. Much appreciated. But yeah. Here's how tree is a functor. So we can define an fmap such that if we do fmap on an empty tree, it will give an empty tree. And if we do an fmap given a function and a tree, we apply the function to the value of the node. We map the left and we map the right. Okay. I don't know if I should continue at this point, I'll be honest, because the stuff I wanted to talk about after this is really abstract. And given that, like, we've been struggling we've been struggling for like the past half an hour, I don't know if I should continue because there's a lot. It really is a lot. What do you guys think?
Well,
Okay. I agree. I absolutely agree. Mm. Task school. Oh my god. Oh no. That would be fun though. Yeah, that'd be pretty cool. Tell you what, I'm not going to go into in detail into the examples I'm going to go over next, but I'm going to talk about, oh yeah, what is Haskell used for? Facebook standards. What is Haskell used for? Like, where did you? Uh, okay. So I'm gonna show you some weird stuff, and then I'm gonna show you some useful stuff, and we'll call it there. Sound good? Okay, cool. All right. So let's talk about FizzBuzz. Now, you might think FizzBuzz is simple. You take an array, you have some numbers. If it's a multiple of 3, you print fizz. If it's a multiple of 4, you print buzz. And if it's a multiple of 3 and sorry, it's just a multiple of 5, you print buzz. And if it's just a multiple of 3 and 5, you print fizz buzz. Simple, right? Well, no, in Haskell you can do some really weird stuff. And here's an implementation of FizzBuzz in Haskell. Oh god, what the hell is going on here? Well, I'm going to skip over most of the details because there's a lot of stuff that goes into this. But essentially what's happening is the first line will return something called a maybe, which is a type that contains a thing or nothing. So it can either contain, say, a maybe int would contain either a just int a just int, or oh my god, okay. So a maybe int would either contain a just int or nothing. So one example where this could be useful is, let's say I divided by 0. I could define a division operator that takes 2 maybe integers. And it takes 2 maybe integers, and if the second integer is 0, it will return nothing. Otherwise, it will return just thing divided by just other thing. Anyway, so what this does is that this is a function that will, when given an integer, it will convert the integer to a string that is either, it will convert the integer to a maybe string. If it is a multiple of 3, it will convert it to maybe fizz. Well, this function will convert it to maybe fizz. If it's not a multiple of 3, it will give nothing. So there you go. So what this does is we basically chain the outputs of these functions together. So this is one function right here. And if you feed the number into it, it will return. If you feed a number into it, it will either give fizz buzz, or nothing. Well, just fizz, just fizz buzz, or nothing. So if I gave it 2, 2 is neither fizz, 2 is neither a multiple of 3 nor a multiple of 5. So it will return nothing. However, if it's a multiple of 3, this will return fizz, this will return nothing, which when combined together will give fizz. Now then, this stuff right here, okay, I'll just skip ahead. There's a lot of, it's the superposition of fizz and buzz. Sean's got the idea right, but there's a lot in the implementation that I'm not going to go over. Anyway, so essentially what this does, this function right here, it takes an integer. This whole thing will take an integer n, and the n will split across these two functions. So n will get converted here to a maybe string, and n here will get converted to a okay. That's not correct, but is it? Okay. So the idea is, what this essentially does is that it will feed n into here and feed n into here. Show basically converts n to a string. So after that, you have what from maybe does, this function right here, is that it takes a default value and a maybe value of the same type. And if the maybe is a nothing, it will just give back the default value. And if the maybe has something in it, it will return the something from that maybe. So what happened, how this line, all the way back, how this line actually works is that you'll basically get from maybe string and a maybe string that contains nothing, fizz, buzz, or fizz, buzz. And if it's nothing, we know that if this part returns nothing, then we know that it is not fizz, buzz, or fizz, buzz. So show will return the string version of that number, and it will, that'll be, so that'll just give a string of that number. However, if you put in 3 or 5, or any multiples of 3 or 5, this will output to maybe fizz, maybe buzz, or maybe fizz buzz. And we know that from maybe, if there is a value in the second maybe, in the second argument maybe, then it will just take that, return whatever's in there. So if the stuff in here is fizz buzz or fizz buzz, it'll just take it out. So this is a function that, given a number, will return either its string version or fizz buzz or fizz buzz. Fun. Look at how concise this is. This is precisely why functional programming is so powerful. So this whole going back to this whole idea of extraction, right? You can just, it's really, once you know how to use functional programming languages, you can really use them to express like really abstract ideas that become really useful once you apply them to certain situations. So you can just say, hey, I want to combine, I want to take a number and make sure and apply these rules if they satisfy them. So it's a pretty powerful thing, functional programming. Now then, so there's a whole bunch of mathy things that go into functional programming that make it work like it does. And I don't really know how to proceed. Let's talk about I/O. Print stuff. So, in Haskell, printing things is really hard because, printing things is not really hard per se. Understanding how printing works is really hard because functional programming inherently does not like side effects, right? So, because of that, it's difficult to understand how a functional programming language can implement side effects. how functional programming languages actually do that is with something called monads. Monads are a really complicated thing to explain because they are an abstract thing, and it's really difficult to understand unless you like apply it to something. So let's talk about a monad called IO. So a monad is essentially a value that's wrapped in a thing that can be applied to a function that takes the value inside and applies it to, gives it other wrapped things. So it's a way to keep a value wrapped within a certain context. So what we can do with that, that's a really powerful idea actually, because what we can do with that is IO takes IO functions within the IO monad, basically allow you to pass values around while not having to worry about all the side effecty stuff that goes on with the command line. So here's an example. If you run this, well, just do it. Copy this into your REPL and try it out. And let me know what it does. Holy crap. Yeah, it is. Sorry, William. Sorry, everyone. Give me a second. Let me change that real quick. There we go. Try that. Yeah, that's exactly what it does. So what this program does is that it'll what getLine does is that it'll take whatever input is from that comes from the command line and it just prints it. So I'll explain what the hell this is. So this is called a bind operator. And getLine is a function that returns an IO monad that contains whatever you typed in. So yeah. So when you type in something into the command line, you have to use an IO monad. You have to use IO in order to interface with the command line, because remember, we're functional programming. This is functional programming. We don't like side effects. The IO kind of hides that away from everything. So when we get line, we have to when we get anything from the command line, we have to abstract. We have to put it and stick it in this IO monad so we don't like go crazy and not know how to deal with anything. So what the bind operator does is that it takes the value that getLine returns in the IO monad, and then it shoves it into this function put string line. And that'll take IO of string, and that it will take the string and then it'll stick it into the put string line function. Yeah, it's like piping. This is probably and and this is probably like the most important idea to take away from functional programming, because I mean it's literally in the logo. And yeah, monads are just incredibly powerful. You can do a lot of things with them. They're basically like they're basically how you get side effecty things in a functional programming language that doesn't normally have side effects, because you can wrap all those side effects inside like its own context and not have to worry about it. Yeah. Okay. More about I/O. So here's basically an explanation of what I just said. Get line is a function that takes no arguments and outputs an I/O of string, and then put string line is a function that takes a string and prints an I/O of nothing, because it returns it doesn't return anything. Well, it returns an I/O of nothing, but we just want it to do something. So yeah, we can actually daisy chain these binds as well. So this code doesn't actually work, but this is just a hypothetical example. Let's say I wanted to get a line to read a file, to parse the file, and then to print the result to the command line. So what this program would hypothetically do is that it would enable you to look up a file and then process that file somehow and then print out the output. So get line would get a string, and then that would pipe it to read file, which would look for the file using that string as the name of the file, and then it would return the file's contents, presumably, and then parse file takes those file contents and does stuff to them, and then outputs some other string, which you could print to the command line. Here's a syntax for do. Do basically lets you put all of this crap, monad crap, in like multiple statements. So here's some equivalent code. This will just ask for your name, and it will print out hello, your name. I'll explain the code down here first, because that's what we're familiar with. So put string line enter your name does not return anything. So we only need to use this operator, which doesn't pass any information. So put string line enter your name, get line, and then this is a lambda function that prints out the output of get line. What I can do with the do function, the do, however, is that I can just do this, and then pipe get line into a variable, pipe the output of get line into a variable called name, and then I can print out that variable name. Yeah. Okay. Here's the last challenge for today. So based on this function here, try writing a function that will prompt the user and then return the string. And I didn't mention this before because, well, I didn't mention it before, but to get out of it, you can return out of a do block by typing return. So that's how you do that. So try writing that function. See how that goes. Okay, I actually have no idea if Kylie and Tang are still here, so I'm gonna continue. But yeah. Oh, well, hello. Thank you for continuing to follow along. It's okay. It's kind of my fault, honestly. It's a lot to take in, but all right. Well, I'm gonna show the code now. So, prompt takes a string and outputs a string. Oh, I should have specified. Okay. Oh my god. So if we want to vary the text that we put in, so we give it an argument t. T is text. So what we want to do with that text is we want to print it to the command line first. So we put string, and then we put string t, and then we do out get line and return out. Yeah. Okay. That was pretty exhausting. Yeah. It took me a long time to put this together because I struggled to understand the concepts going into this as well. But I have a list of sources here if you'd like to look at those. These are all pretty nice, and they really did help me a lot when I tried putting this together. But yeah, I apologize for not like considering the for coming up with a better way to explain this stuff. I agree that this should definitely be a series because there's a lot of concepts here that are just like that take time to digest for sure. But yeah, that's basically it. Thanks for sticking with me for the whole way without knowing what's going on. All right, I'm going to stop recording now.